So conditional statements are where logic starts to get a little weird because now we're having an order to the statements. The statements are holding different positions. And P and Q is the same as Q and P. P or Q is the same as Q or P. The order you write them in doesn't matter. With conditionals, it matters though. So a statement of the form, if P then Q, or a statement that could be rewritten in that form is called a conditional proposition or an implication. Like sometimes we will say P implies Q. The proposition P, the first one is called the hypothesis. Q is called the conclusion. So if the hypothesis is correct, then the conclusion must be correct. It's true in all cases except the case in which P is true and Q is false. So one of the ways I've heard this described is to think of it as a contract. And one of the thoughts I had is the way my daughter thinks dinner goes. In her brain, caps lock, if I eat enough dinner, then I get dessert. We have this argument a lot. Luckily, she thinks frozen fruit is dessert. If you ever have kids, it really works. It actually is a good dessert, but it's healthy. Yeah. So in her brain, if she eats enough dinner, she's getting dessert. If she doesn't get dessert, this is a problem. I have broken what she thinks is a rule, a promise, or a contract. She fulfilled her part, so I need to fulfill mine. But if she doesn't eat enough dinner, she may not get dessert, or she might. Sometimes I end up giving it to her just because you didn't eat any of dinner, eat something. That's why having frozen fruit is so useful. And cheese sticks, she loves cheese sticks. But so if the hypothesis, if the first part, if P is false, the initial condition didn't get fulfilled, so it doesn't matter what happened with the second one, yes or no. We call that kind of vacuously true. So if P is false, we consider the conditional statement as true because it hasn't been violated, because we haven't met the conditions set forth. Since she didn't eat enough dinner, doesn't matter whether or not she got dessert because she didn't eat enough dinner. So my contract holds because we didn't find out if I was going to follow through. All right, so let's tiff, ta, fa. So if everything's true, it's true. If P is, if P is false, then the conditional is true. So it is only here that we get a false. So if you want, you can think of that as the temper tantrum situation. Because she's actually, if she doesn't eat enough dinner, she actually accepts that she may not get dessert. It's actually really nice because then she will eat enough dinner. Now, in English, there's a number of ways that we will say things. If you're thinking about law school kind of stuff or legalese, sufficient and necessary comes up a lot. And notice like the P versus the Q. These are all equivalent to if P, then Q. And we will sometimes write this with an arrow. So there's my P, and that squiggly thing is my weird Q. So if P, then Q, we will sometimes write as P arrow Q, which is why we'll use the word implies here, because P implies Q. I'm giving one word to each symbol. But sometimes we'll use the word sufficient versus necessary. So P is sufficient for Q, or Q is necessary for P. See, I have, if I eat my dinner, then I get a dessert. Now, because conditionals, the order matters, there are 3 other forms of conditionals that you can consider from the perspective of the first one. And this is what the book had. So the first one is just the normal conditional, if P, then Q. Sometimes it's called standard or whatever. Then converse, inverse, and contrapositive are specific terms that mean specific things. So if you're going to make a cheat sheet, this is one of the things I would put on the cheat sheet, because students will often confuse converse and inverse and just forget how to write contrapositive or what it means because the word's so long. So the converse makes me think of Converse sneakers, which makes me think of moving. And if you look, the P and the Q are moving. They change positions. But the inverse, like the mathematical inverse of a number, is the negative of the number. And you look, there's a not and a not. Negatives. Contrapositive just does both of those. It's converse and an inverse. So they swap positions and get negatives. So we're going to do the truth table for all of these. So this is a very convoluted thing. It can be a little awkward to think through. But I'm going to walk you guys through how filling out a truth table looks and feels. All right, so first I have my negations. So I already filled in P and Q, and this is a table I can type in, so let's remember to do that. So not P, I'm just going to overturn, flip all of P's values as they're written here. So that is going to be false, false, and then true, true. Likewise for Q. Q was true, so now it's going to be false, and then true, and then false, and then true. Now, the reason we have all four of those is we're going to look at whichever two columns we're talking about. The one in the hypothesis position, we're going to think of our first one. The one in the conclusion position, we'll think of our second one. Now, in some of these, we're going to have to think about the columns backwards. But our first one, if P, then Q, and let me go with, like this is 1, this is 2. So one of the ways to work with conditionals is we know it's only false in one case. It's if we have true, then false. So we go looking for that and make sure we put the false there, and then everything else has to be true. So there's our true, then false. So we know here for our normal if P, then Q, there's where our false goes. And then all the rest would be true. Now the converse, I'm still looking at P and Q, but now I'm looking at them backwards. So now Q is my first statement and P is my second statement. And remember, it's true, if true, then false is our false. That's when the contract isn't working. So look for when is Q true and when is P false. And that's down here on line 3. So that's where our false is, and then the rest are true. So this first one, they're both true, so we get true. Then Q is false, and Q is false, so those are both also true. All right, now we're going to look at the nots. So if not P, then not Q is look at these two columns, not P first, not Q second. And we want the TF condition. Wherever the TF is, that is our false. And that is here. True for not P, false for not Q on the third line. So there's our false. And whew, I'm just not able to type at 1:30 in the morning. All right, and now our contrapositive, same thing, but we're looking at the statements backwards. So now not Q is the first one, not P is the second, whereas not Q true and not P false. If true, then false, there's our false. And everybody else is true. True, true, true. Now, interesting thing We talked about this a little earlier, but two statements are logically equivalent if they share the same truth values. So if one of them is true and the other one is true, when one is false, the other is false, meaning their columns are identical, the statements are logically equivalent, which a lot of times ends up translating to they mean the same thing, they're equal. It's just in logic, saying they're equal can sometimes be weird because you're still kind of thinking in words, English terms. But here, if we look, true, false, true, true, where else do I see that? Well, it's not in any of my initial statements because those always have pairs. There's trues and falses, always, double, like even numbers of each one. This one is 3 trues and a false, so it's never going to match these initial single statement, single proposition ones. But if I look over here, and that's the nice thing about the colors, those two have the same truth table column for the same inputs. So those two statements are logically equivalent. So if the conditional is true, then the contrapositive is also true. So if you are sleeping, then you are breathing. Yes. If you are just sleeping, then you are breathing. So if you are not breathing, then we do not call what you are sleeping. So that is also true. Sometimes logically equivalent is 3 lines, but I'm just going to put equal. And check out the middle two. The converse and the inverse also have the same truth table columns for the same inputs. So these two guys are equal. So they mean the same thing. Now in this case, with the words, they are both false. If you are breathing, then you are sleeping. Not necessarily. I can be awake and breathing. If you are not sleeping, then you are not breathing. No, I can be awake and breathing. But the conditional and contrapositive mean the same thing. If one's true, the other's true. Converse and inverse. If one's true, the other's true. All right, so that is kind of like the nuts and bolts with how truth tables work. But the big one is thinking about this if P then Q, this idea of conditional fulfilling a contract. If I fulfill the necessary condition, then I get the result. And that is it for logic. Go forth and have fun with Alex. Hopefully fun. I know.